was about British experience.
Arthur, desculpa, é só para avisar os colegas que eu vou começar a gravar a sessão e quem quiser que desligue a câmara e convinha era que todos desligassem o micro para já, tá bem? Desculpa.
Sim, seria agradecido, senão sem stress. Okay, now, fourth time is the charm, I hope.
Yes,
welcome back.
So, yes.
These online sessions are always awkward in these beginnings. So Fernando was just reminding the audience, which is more than 100 ICT teachers from Portugal, of the first time you were over here in Portugal, talking to us about Great Britain's beginnings in fostering computational thinking in education as a system-wide experience. And if I do believe, Fernanda also told us that today our invitation is for you to talk to us about what is being done in British schools, how is the experiments and the curriculum of computational thinking in its several aspects being worked with teachers, with students at schools. And of course, I have to do these small notes. Professor Barry has a very long curricula, which I won't go into detail. But let's just say that he is, of course, the principal lecturer on computing education at the University of Roehampton. I hope I haven't mangled too much the name of your university. And I think for most of us that are right now in this session, it kind of it does not need to be presented, because for us, Professor Barry is probably one of the foremost contemporary thinkers on coding, education, and computational thinking. And so, without further ado, I'll give the word, the platform, the camera to you, Professor Barry.
Arthur, I think you flatter me very much with that sort of introduction. I'm a school teacher. I spent 18 years working across 4 different schools, much of that time as an ICT coordinator, although my background is over in maths education. And then I made the move into higher education. So I've been working at the University of Roehampton for the last 13 or so years, training the next generation of outstanding teachers. Roehampton has allowed me out to go and do other interesting and exciting things. So as part of the panel that drafted England's computing curriculum, and I've been involved in a lot of the implementation projects over the last, 10, 11 years since we started that work. And that's the story that I'd like to tell you this evening. So something of how we began this journey, and then bringing those of you who've heard that bit of the story before up to date with a report on how things are going now. Let me do the screen share thing if I can.
I believe you can.
Okay, yes, it's about my skills rather than the technology's ability. So I've taken my slides in English and used the machine translation over in Bing to translate these into Portuguese. There probably are going to be some really bad translation mistakes there, but I thought better to show the slides in something approximating Portuguese than you just have to stare at English slides whilst listening to me talking in English. And similarly, at the bottom of the screen, you have fully automatic machine transcription of what I'm saying. It is worth pausing and thinking just how amazing that is, that we have technology which can, yes, translate these slides, but can also listen to the words that I'm speaking, move those from one language into another language, and then display those in real time for you to see. So I think we would forgive the technology a few mistakes there. I'm happy to be interrupted as we go through, but it might be easiest to save questions to the end when you've heard the whole of this story. So let's make a start at any rate. So let me take you back to 2010. That's like 11 years ago now. And one of the great guiding intelligences for curriculum reform in England was looking abroad at what high-performing jurisdictions around the world were doing in terms of curriculum change. And so Tim Oates, working then as now at Cambridge Assessment, says that the best countries to look at are those which had taken a coherent approach to designing and developing and implementing their curriculum. And when Tim talks about coherence, he means 6 particular things: the content of the curriculum, how we go about assessing that, the pedagogy, how that curriculum is taught, what we do in terms of professional development or professional formation, the teaching materials that we use, and he talks about the incentives and drivers to make sure that that curriculum is actually enacted in schools. I'm going to take those 6 themes and explore each of those in a bit more detail in terms of what that has meant for the English computing curriculum. The other thing I'd like to say right at the start is 2010. We basically ran out of money. So the government, the incoming government at the time, had taken the view of, we don't want to do all of this work. We're very happy to do the thing that only government can do, but we would very much like the sector, schools and companies and third sector organizations, to step up to the mark and deal with a lot of the implementation. In retrospect, that wasn't necessarily the best idea, but at the time, government should only do what only government can do, seemed the only way to get any change to actually happen there. So let's focus firstly on this idea of the content of the curriculum. And actually what's happened since then is much of the really exciting work has happened in the pre-formal education phase. So for our very, very youngest children, the children before the age of 5, we have this statutory framework for the early years foundation stage, and then non-statutory guidance called development matters, of the sorts of characteristics of effective learning that these very young children should be developing. And if you pause for a moment and look at the slide, aren't these just exactly what we want in terms of the computational thinkers, the problem solvers, the software engineers of the future, people who will pursue a project, figure out what the goal is and figure out their own way to get there, stick at things when they get very difficult, change direction when it turns out things aren't working particularly well, be tenacious in solving the problems that they encounter there. So much of the foundation of what we've come to term computational thinking, we're actually laying before children even use computers at a very, very early age in this early years foundation stage. The new schools minister back in 2010 said he was rejecting all that our Labour government had done in the preceding, it must have been 13 years, and wanted to bring our national curriculum back to the basics of a much smaller curriculum which specified just the minimum entitlement of what all children should be taught whilst at school. And he saw that as being structured very much along a subject by subject line with an identification of the core knowledge that children should acquire. A knowledge-rich curriculum is the phrase that he used there. So much more of a return to a traditional model of education, for good or ill. He decided to replace ICT as a subject. We had information and communication technology on our curriculum, just as I believe Portugal does in secondary education, with a new subject called computing. And he assembled, or he got the British Computer Society and Royal Academy of Engineering to assemble an expert group representing a whole different range of stakeholders there. So you see on my slide here, NACE, the Subject Association for ICT Teachers. We have Computing at Schools, the then new organisation for computing teachers, and lots of other stakeholder bodies there, including some school teachers, some from higher education. There's the old University of Roehampton logo there on the right-hand side of the screen. And he talks about developing this curriculum with some of Britain's most brilliant computer scientists. I don't think he was talking about me at the time. As I say, I'm just a teacher here. All right. We took a lead from what the Royal Society had done in terms of reviewing the state of computing education and said there were 3 elements to this: computer science, information technology, and digital literacy. And previously, we focused very much on that middle tier there, the applications of digital technology. We added to that an understanding of the fundamental principles of how digital technology works, the computer science bit, as well as a really important layer of considering the implications of this technology for individuals and for society as a whole. And I think a broad and balanced computing curriculum should have those three elements to it: the foundations, the applications, and the implications. We start with this noble ambition that a high-quality computing curriculum develops computational thinking and creativity. The computational thinking to understand the world, the creativity to make a fundamental positive difference to that world. And I think this has to be a both-and approach to it. We identified 4 broad objectives, 4 aims to what we were trying to do with the computing curriculum: that children should learn the principles of computer science, the fundamental principles of computer science. They should have repeated practical experience of programming. These are different things, the principles, but then also making the machine follow a set of instructions. They should still be able to appreciate the applications of IT, as well as being responsible, competent, confident, and creative users of digital technology, ready for the future workplace and indeed the future world. The whole curriculum from age 5 to 16 fits onto 3 pages of A4, and respect to our ministers of the time of insisting that this be really trimmed down rather than page upon page of everything that the child should learn, leaving so much of the implementation to schools and saying, no, this is the basics of it. This is the essential core of the curriculum. And there, what you have in a key stage, the whole phase of education fits into sort of half a side of A4. There's probably a lot of emphasis in these statements on the computer science aspects, less so on information technology, less so on digital literacy, but it's easier to specify those computer science elements. There's a strong sense of progression within computational thinking and within programming as children make their way from 5 at least up to 14. The bit that I think is confusing is what happens at age 14 to 16, where we have computing as an entitlement for all children, but they don't all have to take a qualification in it. So yes, they should still be taught some computing at that age, but they don't have to then pursue the exam qualification. They don't have to sit the exam and obtain a qualification. That's left as an elective subject. So government also specifies what's covered in those qualifications as the requirements for the specifications, both the 16+ qualification, what we call our GCSE, and the 18+ qualification, the A level in that. And then we have a market in our exam boards, our awarding organisations. There are 3 or 4 of them, each of whom will produce a qualification that meets this specification and then get schools to put their pupils in for that. I'll tell you a little bit more about how that's going later on in this. Okay, which brings me rather nicely onto the topic of how you go about assessing whether children have learnt the content of that curriculum. So that was our job as the drafting panel. This is what children should learn. Now, off you go, teachers. Off you go and teach this to young people. And there is, it turns out, rather more to it than just writing that specification. Figuring out whether they've learned it turns out to be really important, because so much of what happens in our schools is driven by the assessment systems in place. And I think that's definitely one of our lessons learned. Getting assessment right from the start would have, I think, avoided a lot of the difficulties in terms of implementation. So we have an attainment target. There's a statutory requirement that the national curriculum includes a statement such as this, the details of what achieving these requirements would look like. And all it says here is that by the end of the key stage, the children should have learnt the things that they have been taught. It's as simple as that. What that looks like in practice is rather more complicated. So myself and one of my colleagues at Roehampton Peak Camp went off and produced the list. We took the content of the curriculum and broke it down into the individual sentences or clauses there so that teachers could tick off or pupils themselves could tick off when they could do a thing, when they could assemble some evidence of, yes, I have learnt that thing that I've been taught, or the teacher could say, yes, my pupils have learnt that. And tracking that over a period of time gives a strong sense of whether a pupil is meeting the requirements that the curriculum specifies. We had in the past this really complex system of giving levels of attainment as a child progressed through the national curriculum. This was abolished with the curriculum change and replaced by this sort of simple statement. What then appeared was, what we then realized was we needed to provide questions to help teachers assess that. So much of what we do in computing can be assessed through project work, but it turns out questions are also really very good at doing this. And our Macintosh Commission recommended developing a national item bank, and we've done that for computing. We've produced about 12,000 multiple choice questions for schools to use, by schools, for schools to use for free to test their pupils' understanding of the big constructs of that computing curriculum on within lesson or an end of topic basis. I think that's been really useful work. We started with project specifications. So this was for the elective 16+ qualification, our GCSE. Can you create a program which plays this really quite fun game here? You have to guess a 4-digit number and the computer tells you how many of the digits are right and in the right place. It's a really nice programming task, and I think a suitable capstone for that sort of, what is that? That's going to be about 12 years of formal education following the computing curriculum by that point. The problem is, once you make a specification, a problem like that public, not everybody, but lots of young people go and post their solution over on Stack Overflow or the student room or GitHub or somewhere out there on the internet. And then other students, rather lazy students, come along and find those solutions and hand that in as their own work. So this sort of, there is a project task, was open to lots of abuse. And so our exam regulator said, enough of this. We need to get away from this idea of there being a project component to this. Yes, there should still be some practical programming, but we want to move away from that being assessed through project work. So they said it's up to these exam boards. They could either assess it through a written exam, or they could do an on-screen test, but we don't want any more project work in computing at that point. And that seems to me such a shame. There must have been a better way to do it. And so now all schools have to do is say, yes, pupils have had the opportunity to do some practical programming, tick a box. And then the boards come up with a way of testing that in the exam, which I feel is very unsatisfactory at the moment. Let me turn my attention now to how we go about teaching computing as a subject. I think the first thing to say is the emphasis has to be on these big constructs of computational thinking. We're wanting pupils to really develop things like logic and an understanding of algorithms, and taking a problem and breaking it down into smaller parts and looking for patterns and being able to generalize. And yes, working with layers of complexity there. Much of this I think I've seen in ANPRI's document there. Alongside these big constructs, we think there are also a number of approaches that constitute computational thinking, of tinkering with things, of trying things out, of being creative, of making something that wasn't there beforehand, of, yes, fixing things when they go wrong, of persevering when things get difficult, and of collaborating so as to being able to work together on a project. I'm conscious that my internet is a little bit flaky still. We've recognized that programming itself is a two-step process. Firstly, figure out how to solve the problem and then express it as code. The two really should go hand in hand there. The method to solve the problem and then the expression of that as a solution. So whilst the emphasis may be on problem solving, on computational thinking, there really has to be a strong emphasis on being able to write and test and develop working software. In terms of coding, I think we're looking for a range of tools. With our very youngest children, we'll start with the little B-shaped robots of creating very, very simple sets of instructions using just those 4 buttons, and then programming on screen using a tool such as Scratch. and then moving into text-based programming when our pupils move up into secondary education. And Python seems to be the language that we're using for that for the most part. Think we may be back. We'll see. Okay. There's some really good evidence that certainly in higher education, those who are teaching computing take a very pragmatic approach. They're very ambivalent, very agnostic about the best method in which to teach programming. So there's a whole range of techniques. And I think that's one of the lovely things about our subject, that teachers are figuring out for themselves. This seems to work for me with my class. We're a very young subject, and I think there's so many advantages that we benefit from that. The new National Centre for Computing Education has made some particularly good recommendations about this is how they're approaching the teaching of computing. And this is relatively late in the day that we've actually got guidance on how to teach this subject well. And, a number of really, really helpful ideas about, yes, making projects, about, yes, focusing on pupils' misconceptions, about this idea of start with the abstract idea, then make this concrete, make this tangible, about using a range of different methods, about, yes, collaboration as an important approach to that. I'm hoping this is still working. Let me talk a little about professional development, because this has been one of the real challenges for us that we've had, whereas every other subject, particularly in primary education, teachers learnt about when they were at school. Implementing a new subject such as computer science as part of the computing curriculum adds a whole layer on top of that, of expecting teachers to teach something that they may not have learnt themselves in their school days. It's a fast-moving subject, for one thing. It's also one that very few, not all teachers have an academic background in. So addressing that has been really important. And we know the quality of any education system cannot exceed the quality of the teachers working in that system. So for a lot of the early days, our work said teachers have a good range of pedagogic skills. They have competency when it comes to using technology. What they lack is the subject knowledge of computer science. So most of the early professional development work that we did focused particularly on developing that understanding of computer science as a subject, of providing them with that subject hinterland there. In fact, before we even wrote the national curriculum, we'd identified the subject knowledge that new teachers of computer science ought to know about before they began their training as computing teachers. And this, I think, has provided a framework for much of the professional development that we did in the time before the establishment of the National Centre for Computing Education. Talking of which, so this was set up after the budget in 2017 with a recognition that what we had done was, I think the phrase was patchy and fragile. To make sure that our computing curriculum was a success, it needed serious funding from central government to do a number of things. Firstly, to make sure that teachers received the professional development that they so clearly needed. Secondly, to provide a community of practice to support the development of teachers being able to share materials with one another, to produce the resources that teachers needed to be able to teach the subject well, and also to address the huge issue that we had in terms of the gender imbalance in the subject. I'm not sure whether any of this is coming through at the moment, and I don't think there's very much I can do about this. So one of the things which the National Centre has done is to establish a system of professional development for teachers, but also qualifications for teachers to work towards, both for those in primary school and secondary school, and particularly for teachers of that elective GCSE qualification, so that we should have, by the end of its 5-year term, 8,000 new teachers of computer science at GCSE. And so far, the story is a very, very positive one. Here are some of the numbers from their report as to what they have already achieved. 7,600 teachers benefiting from the professional development that's been available through that centre. Let me turn now to teaching materials. Again, in the early days, this idea of government should only do what only government can do. So much of this was done by commercial publishers producing schemes of work and then selling those into schools, as well as lots of work by teachers themselves. Government funding then produced the barefoot resources, which were intended as exemplars for teachers to give examples of how the subject could be taught in school. But these have proven to be really very, very popular. Lots of teachers using those as the basis of their scheme of work. And now with the National Centre, we have a much more comprehensive, detailed scheme of work. You'll see the lovely train line type diagram there, which takes pupils right from year 1 all the way through to the end of year 11 to the age of 16 with half-term by half-term units of work on computing and a very detailed concept mapping of how those resources relate to one another. Isaac Computer Science, part of the National Centre there to address specifically teaching at A-level.
Something is going wrong.
Don't use the microwave.
Nós fomos tocados por microfone, por micro-ondas. Okay.
Acho que o professor saiu, não foi?
Sim, Fernanda, estás a partilhar o ecrã?
Não,
Deixa-me
não
ver se
é.
na lista.
Alguém está a partilhar o ecrã, mas não sou eu.
Eu também não, acho que não estou. Ok. Pronto. As conexões às vezes travam-nos e ele por acaso estava a notar na parte da tradução automática que estava ali a falhar um pouco. Vamos um pouco.
Eu penso que era o professor que estava a partilhar, porque aquele dizia people em inglês.
Desculpa, não estou a ouvir, Marco.
Eu penso que era o professor que estava a tentar
sim, também posso
ser, porque aquilo dizia people, o nosso time está sempre em português, não é? O dele deve estar em inglês.
Estou aqui a ver se eu encontro lista de participantes.
Entrar.
Welcome back, Professor. Or at least I hope so. Ok, isto não é grande coisa. Deixa-me ver se consigo de outra forma.
Mas enquanto ele chega, se calhar podemos ir.
I don't know how you heard. I don't know what would be helpful. I'm worried this is all going to drop off again. But what would you like me to? Would you like me to talk any more? Where do you want me to go back to, if so? Or do you just want to do questions?
Actually, for me, it's being an extremely interesting talk. You were waylaid by the microwave when you were speaking to us about the train line. The train line.
Oh, wow. You got lots more than I thought you had.
Yes, we did.
Okay, Right, that's good. That's really good. I'm amazed that it carried on that long. It was really plenty. Yeah.
As for me, if you wish to proceed from there, I mean, it's fine.
Yeah. Okay, let's go for that then. This will be not very much longer. We're nearly there. Okay, thank you so much for your patience. Okay, here we go.
I can remind the audience. Any questions? Fine. I'll translate it.
Oh, I will do the screen share, because otherwise it's just me looking at the slide, isn't it? Okay, PowerPoint slide. There we go. Okay, so this is the train line thing. So as I say, the new National Centre has done this curriculum resourcing incredibly well. They've got some of the best teachers in the country working on the project of producing really high quality resources for free for schools, all licensed under a Creative Commons Open Government license. So this phenomenal work. With a particular way of doing it, we lose a lot of the freedom that we'd originally had by adopting this, but it does it very, very well. I say to my trainees at Roehampton, you will not be able to do it better than they have done yourselves. And some of them see sense in not doing all of this lesson planning themselves. Beyond that, we have Isaac Computer Science, again part of the National Centre's work, which is focused on students themselves doing this really hard 18+ elective qualification and providing really good support and a really good set of questions for those students. There are other phenomenal projects. I hope all of you on the call are familiar with the fabulous BBC Microbit, this tiny wee circuit board computer, a 25 pixel display, 2 input buttons as well as an accelerometer, getting children really excited about making things with computer hardware rather than just on screen. And then, of course, sitting above that, there's the Raspberry Pi. Yes, they were made for children, for young people learning. I think we've seen lots of them being used by an older generation of learners. But you're seeing encouragement for people to use that as a basis for A-level project, these 18+ projects, and advice from the computer laboratory at Cambridge for this is a really good platform for you to make something on if you're interested in coming and studying computer science at that particular university. Let me wrap up, please, whilst we've still got internet, with some of the incentives, some of the drivers, how things have been going. Last year was the very first year where we've met our recruitment target for new teachers of computer science. So consistently over, 7 of the last 8 years, we've under-recruited new teachers of computing. If you've got a good degree in computer science, there are lots of other really appealing careers for you to go and follow. 2020 to 21 was the first time we've actually got as many teachers as we wanted to recruit. Fingers crossed that carries on. The key message of this is that this is for everyone. Computer science should be something for everybody to study. And that's the advantage to putting it as part of a national curriculum. That once it's there in the curriculum, everybody gets to learn about this, rather than just those who are interested or those who happen to have parents or those who go to the right sort of school. This is an inclusive curriculum for everybody to follow. And yet, what we see at the moment is the schools that offer that elective qualification at 16+ tend to be in the most affluent areas of the country. And I think we have to do something about that. This should be a flat graph, ideally at 100%, that all schools are offering a GCSE, this 16+ qualification in computer science. Not all pupils will take it up, but it should at least be an option for children, irrespective of which school they go to. The numbers for taking up the qualification have increased. So we started at a very low base level back in 2013 and then fairly rapid rise over the following 3 years. It's sort of leveled off a little now. 2019 was the highest number of entries. The blue graph is what happened to the old ICT qualification, which ministers removed from the list of what was available. So yes, it carries on in...
Sorry. We can still see you and hear you, Professor. or maybe not.
Oh. Okay, that's fine. It just says it's reconnecting. Okay, I'll carry on talking in that case. Okay, where was I? So yeah, so it carries on in Northern Ireland and Wales and Scotland, but in England we've abolished the ICT qualification. One of the problems we have is that it's predominantly boys choosing to take the qualification. Computing is there right at the right-hand end of the table. Only 80% of those taking it are boys. 20% of the entries come from girls, and that's not right. So we need to do much more to promote the subject as one which appeals to all of our learners, not just boys. At A-level, the picture is, I think, more positive for A-level computer science. We've seen a very, very steady increase in this. It's a hard qualification. It's still not yet required as an entry for degrees in computer science, but we've seen a steady year-on-year increase and gradual improvements in the number of girls who are taking that, although this is still pretty abysmal. About, what is that? That's about 13% of last year's entries.
E parece que estamos outra vez com ligações. Entretanto, colegas, se tiverem questões que queiram colocar, podem passar para mim que eu tento traduzir, ok?
Bem, eu queria era falar inglês, mas olha, eu tenho uma questão que tem a ver com o seguinte: como é que nós temos acesso ao material gratuito em inglês? Será que só mesmo os professores ingleses?
Eu coloco essa questão.
Ou nós também podemos ter acesso para também nos ajudar, não é?
Eu reparei que ele sublinhou a questão do Open Licensing e da Government License. Há pelo menos um recurso que é o Barefoot Computing, que isso é totalmente aberto. Eu uso.
Obrigado.
Professor Miles, we wait, of course.
Os métodos deles são muito diferentes dos nossos e a maneira como eles ensinam é totalmente diferente do nosso, o que faz com que haja uma disparidade da maneira, como é que eu vou dizer, de ensinar, de fazer as coisas, porque eles ensinam os alunos a buscar as respostas, a direcionar, o que é diferente. Eu pessoalmente eu estranhei porque já lá estive e tive dificuldades em perceber isso e revi, quando ele falou, revi essa situação toda. Principalmente na faculdade, baralhou-me completamente o sistema deles. Eles têm um sistema completamente diferente. Eles em qualquer sítio ligam o computador e discutem com o professor o seu projeto. Não têm barreiras entre professor e aluno, coisa que nós cá temos muitas barreiras e muitas dificuldades.
Mas ele também pouco passaram por várias fases, uma fase em que trabalhavam por projetos, depois mudou o governo, era por questões e testes.
Exatamente.
Acaba por ser também um bocadinho as fases políticas que nós temos passado, mas sempre
Entretanto, professor,
4 anos atrás do percurso, assim, Arthur.
o professor está de regresso, portanto, Professor Miles, Professor Barry, welcome back again. Do you want to share with us anything else, or can we go to questions and discussion?
Questions is fine whilst I still have some connection here. Thank you so much. And again, my apologies. This has been such a frustrating experience.
No problem. I actually confess, every time I do a virtual session, something wrong happens. So, and anyone who has worked with me knows exactly this problem. It's I mean, it's like we feel like we're living in the future, but the technology is always not quite there yet. So,
right.
From our participants, we have basically 2 questions. One, which was asked by Marco Santos, is about the resources you've developed, barefoot computing and everything else. I've noticed that you've underlined that they are openly licensed and with open with Creative Commons licensing and government licensing. And Mark's question was about, are these resources specifically to be used in Great Britain, or can they be used globally by any teacher which is interested in using them?
Yeah, so they can be. They've been written with the English computing curriculum in mind, but you know, Scratch is pretty much the same the world over, and teaching a child about repetition in Scratch isn't because of the English computing curriculum. Anybody who's programming in Scratch will want to learn about repetition. So the stuff that we've written under with government funding has to be released under this liberal license. It's called the Open Government License. So you can take that and translate it into Portuguese if you'd like, as long as you acknowledge the source. There are some conditions about images, but I think they're still fairly relaxed and fairly liberal. So it's worth just checking the terms of the license. My understanding is, as long as you say where you got it from, you can do what you want with it. And I really encourage you to do so. This is about adapting rather than adopting.
Adapting rather than adopting. I just love that expression, because
it may not translate well into Portuguese, of course.
No, because I mean, it's the openness. I mean, it's. I believe one of the structural things about your talk is the progressive openness of the computing curricula and approaches, etc. And one thing I would like to underline is, maybe correct me if I've misinterpreted you, but I believe you began your journey, because this is a journey for you, for us, and we are now also in some very crucial stages of our own journey in computational thinking and in coding and robotics, and especially we are also looking into skills, not as just literacy, but in terms of deep mind skills. But one of the things that struck me in your presentation was how you've began with lots of sometimes diffuse ideas, lots of experiences, and then you've coalesced into a path, into a learning path. Why? I mean, I think we know the answer. The answer, of course.
I think that's very perceptive of you. I think as a system. I mean, the Royal Society's 2017 report was pivotal, literally pivotal in this. In the first 5 years of this was very much a sort of, let's try lots of different ways of doing it. Let's figure out what works. Let's just produce loads of resources. Let's have a go at this. And that's great. You know, teachers just rolling up their sleeves and getting on with this. And then the Royal Society takes stock and say, what has worked well? And as I say, the key phrase was this patchy and fragile, that there were some schools that were doing this very, very well, but it wasn't sufficiently well embedded to feel secure, that in order to do it properly, you can't just keep relying on teachers' goodwill and their spare time and, oh, this is this is what I do with my class. Try it with your class. You need to do this seriously. And the 80 million of central government, 80 million pounds of central government funding made a huge difference to that. Assembling a core team to say, this is actually the best way to teach the subject. This is what the evidence says works for this. These are the resources that we've tried out in schools. We've tested these. We've got some of the best teachers in the country working on producing these. I think that's made a huge difference to making this now stable. So yeah, it's not forced on any school. You don't have to do it their way. Schools have a lot of autonomy, freedom over the way they're doing this, but producing that material, producing those training courses and making those available for every teacher of computing has helped tremendously, I think.
Actually, that's a very huge step, because you began with a bottoms up approach, every teacher, and then you have not shuffled that work over, and you've picked up that work and used it to structure and to find a coherent way to reach all schools. Because as you've mentioned at your last slide, I think it was your last slide, this is for everyone, right?
Yeah, absolutely.
So, caros colegas, dear colleagues, anyone has some questions, some comments that would like to put to Professor Berry?
Sim, eu tenho uma.
Yes, Fernanda, please.
Quando fui da outra vez e durante alguns anos, o professor separava muito as TIC do pensamento computacional, e agora parece-me haver um caminho em que se podem trabalhar as duas, ou até em conjunto, pareceu-me haver esse percurso. Se eu entendi bem, porque às vezes era um bocadinho rápido. Porque ele fazia questão até de ter um esquema em que dividia isto é daqui, isto é dali, e agora já esbateu essa... Era um bocadinho...
Okay. Vou tentar então condensar.
Ele fazia uma separação muito clara das coisas, e agora parece-me haver um percurso em que se conseguem trabalhar as duas situações, o que é TI e IT e o que é Ciências da Computação.
Okay.
Fernanda, peço desculpa. Fernanda, sabes porquê? Porque eles, principalmente na parte da... não no secundário, mas na faculdade, porque eles dão a programação, por exemplo, programação e tudo o que tem a ver com computação, eles acabam por dar uma série de skills, de
competências básicas,
de interações, em que misturam tudo junto, estás a compreender?
Sim, é o que nós estamos a tentar fazer agora aqui,
sim,
mas que não é um percurso muito defendido ainda, e pareceu-me haver uma evolução nesse discurso do professor Miles, e era isso que eu queria que ele esclarecesse.
So, if I may,
Yes.
so Professor Berry, Fernanda was pointing out that a couple of years ago, when we've met, you were happily over here, and without legs and microwaves. Sorry. She pointed out that a couple of years ago, there was in your discourse, in your way of talking, a clear separation between IT skills and computational thinking skills. And maybe we are misinterpreting you in today's presentation, but we felt that today you were pointing out more of a melange, a mix between those two areas. What is it? Is it an evolution in ways of thinking about using IT skills and conjoining them with computational thinking?
That's interesting. I don't know as my thinking has changed significantly over this period. So I think a diagram of the foundations. I see the computer science as including the computational thinking and the programming in there. I think within that middle tier, the IT skills tier, I'm thinking about word processing and making presentations and making digital video, digital media, and all of those sort of getting useful things done with a computer. Now, I think if you've learned how to think computationally, if you have an understanding of these fundamental principles of how we solve problems with computers, then you also get good at that middle layer, because you've got a really good set of problem-solving skills there, that you know that if I'm making a presentation, I've got to think of the story I want to tell before I start throwing media and text and so on onto PowerPoint. So I think you can apply computational thinking to IT skills, and it's a really good way of getting stuff done on a computer. That said, for me, computational thinking is about finding automatable solutions. It's about finding a way to make the machine solve lots of problems like that, rather than just being able to get, do really good things with a computer. It's about repeating that on an automated basis. I think that's my current position. I'm now very curious if that's very different from what I said when I was with you 4 years ago. Oh, I wonder. I will have to go back and read it.
Possibly not, but I think you made it quite clear that there are levels, right? And that at the top, at the foremost level, at what really infuses yours and ours and our look at computational at computing, etc., is precisely that, the higher goal, Turing-like, of automating most things. But I am interpreting. Sorry, I'm getting a bit tired. I'm interpreting. I believe these skills are also useful for those of us that won't go that far. And that's, I believe, one of your key messages and the whole computational thinking is that we are looking towards the utmost, the computational thinking, the automation, etc. But it is so useful for everything else in our lives, right?
Yes. In English schools, and I suspect in Portuguese schools, teach lots of things because they are worth learning. We teach music and poetry and art and lots of lovely things like that, not because we need more professional musicians or professional poets or professional artists. Perhaps we do, but we include them in the curriculum because they give you a lens through which to understand the world, an appreciation of creativity, and the means to make a difference to that world. This is about, understanding and creativity. And I think we should teach programming and computational thinking for the same reason. Some of our students will go on to become software engineers, but they all should have an understanding of how this technology works and the ability to turn it so that it does what they want, rather than merely what its engineers, its developers thought we would want it to do.
Since you've mentioned the arts, I have to mention this. I was mind blown by one of your latest shares on social media, which was using processing, P5.js, to recreate op art by Bridget Riley. For me, it was mind blowing because I'm an arts teacher at the origin. So any project, any approach that really crosses computational thinking, computational science, and the wide view that the arts bring to us, I mean, it was mind blowing. So for me, I'd like to thank you for the inspiration.
Thank you. Invite me back. I'll do another one on that, maybe with better internet. I think we have been too narrow in the problems that we get young people solving with computers. So we may get them to make a game, or we may get them to make a little animation, a little cartoon, or very often we just get them to make problems or make programs which don't do anything interesting or useful. This is about creative expression. Yes, solving problems is important, but so is making something with this technology. Pappett's great insight from the 1980s. And the context for this problem solving, I think, is really interesting. So, we talk about computational thinking, but it's about solving problems and understanding systems. And those problems, those systems can come from the arts, can come from other STEM disciplines. They don't all have to be about putting numbers into order. Really, they don't.
Fernanda, you were trying to say something?
No.
E que achas, encerramos? Falamos um pouco mais?
Podemos só perguntar se, porque eu acho que também essa questão também está muito patente na apresentação dele atual, que é a importância de depois trabalhar o pensamento computacional com as linguagens de programação por blocos ou sem blocos, dependendo da idade, não é?
Okay.
Porque já não se fala só no desplugado, mas há também uma evolução de se é preciso fazer, depois tem que se passar para os blocos de alguma forma.
So, Professor, Fernanda was pointing out something that she detected or interpreted from her presentation, which is, how can I put this nicely, the levels of coding, beginning with unplugged, then going to blocks-based coding, and onwards to more traditional line-based coding, written text languages. So, why?
Okay. So in preschools, in nurseries, kindergartens, there's a strong sense amongst practitioners, amongst teachers, of children have too much technology. So yes, there are really good nurseries where children are using iPads or lots of other digital devices, but a lot of these settings are very reluctant to have more screen time. So solving problems with big blocks of Word, or putting sweets into different categories or sharing sweets out, is that sort of physical manipulative activity. We can do so much computational thinking that way, thinking about how to solve a problem. Yes, no automation coming just yet, but at least those problem-solving skills being developed at that early age. The text-based programming isn't necessary for the development of computational thinking. It's still computational thinking if it produces a scratch program at the end. You're still automating a solution to a problem that you've had. There are times when Scratch and other block-based languages become frustrating for the learner. They want to work on a canvas bigger than 480 by 360, or they get fed up of dragging blocks into place there. It's still a Turing complete language, but there are frustrations which sooner or later get in the way of that creative expression. When we wrote our curriculum specification, we said before the age of 14, children should have learnt at least one text-based language. And the 16 plus qualifications say the programming has to be in a text-based language. So we forced the issue that they have to make the transition from blocks to text during secondary education. Were we right to do that? I'm not sure. I think if we want pupils to be able to use their programming later, rather than merely develop computational thinking, then they're going to have to use a text-based language, JavaScript for our lovely P5JS work, or Python for lots of the data analysis that they might want to do if they're studying social science or the sciences when they get to university or in their first jobs. So a text-based language is a useful thing rather than merely something which helps you understand the ideas.
I will just like to point out the broadness of what you have just said to us. The idea that we need to go beyond blocks-based languages not because they're useful, but because they allow our students to grow even more, right?
So there are studies, I think, with predominantly in the US, that children do better with block-based languages. Shock, horror. It is easier to understand the big ideas in a block-based language. There are fewer things to keep in your head there, cognitive load and all of this. But once they've got the ideas there, then make the transition, I think, to a text-based language. But my advice to my trainee teachers is stay with blocks for as long as you can, because it's still a very, very expressive language.
And yet, do not fear the complexity, right?
No, fine.
So, people, any more questions? Anyone wants to join in?
Yes, if I may.
Yes.
Luís, but
Hello.
be my guest.
Hi, Professor Miles. I'm one of your students from Azores.
Oh, it's lovely to see you, Hilary. I don't think you describe yourself as a student. Colleague from Azores.
Okay, a colleague from Azores. And it's quite refreshing to hear you talk, because I believe you made a speech for a different kind of teachers. Now you're in the computer teachers, and you're speaking with people that have a little bit of trouble. And I include in that group, distinguish between computer science and computer thinking.
Okay.
Because for us, it's something natural. We go and say, of course, algorithms, we go and do it on a computer. And we solve problems on a computer, and we play with Scratch and everything else. But computer thinking is more than that. Now, my question is, how can we make that transition with a kid, a student? Because it's not about, okay, if he knows how to program, he knows how to program, but he might not know how to computer think. How can we? I don't want to say test him, but how can we, at the end of the program, say, okay, you might not work on a computer, but I know that you developed your solving skills.
So there are things I'm quite skeptical of some of the approaches that there are to teaching computational thinking. So there's a very famous one which says, could you please write down your recipe for making a jam sandwich? And children write out the steps that you have to follow to make a jam sandwich, and then the teacher acts it out, and it goes horribly wrong because they've not listed all of the steps. You've seen this? You're familiar with this? Okay. I don't think that's teaching computational thinking. It's teaching something about precision in language and planning ahead. And these aren't bad things to learn. But I don't think we make the link from that to automating a solution. If what I'm doing is finding the best way to make a whole host of sandwiches, you know, if I'm catering for 200 people and they all want sandwiches, then I've got to start thinking of a way to automate this process around, you know, a family of 20 people helping out in the kitchen or whatever. Or if I'm making a machine in a factory to make jam sandwiches, heaven forbid, then it becomes computational thinking. So I think the way I do this is to say, how would you program a robot to solve this? Or how would you program a computer to solve this? Or how would you make a machine figure out this, rather than just how would you do this? My favorite example is the guess my number game. So we do this in maths lessons. I'm thinking of a number, you can ask me lots of questions about it. In a maths lesson, you want lots of really varied questions like, is it a prime number? Does it have a 3 in it? Because that really extends their mathematical reasoning. In a computing lesson, I want them to think of a systematic, I think that's the key, isn't it? A systematic way of solving this, of making the computer play the game. So I would do, is it less than 64? Is it less than 32? Is it less than 48? A divide and conquer approach to it. So we're looking for a repeatable way of solving the problem rather than just solving the problem. So yeah, learning the building blocks of computational thinking, learning about algorithms and learning about abstraction is great, but it has to be put to use in finding that automatable computational solution. If you'll allow me, computational thinking without the computation is just really thinking.
Any comments, Luís?
Thank you very much.
Por favor, continua.
Each session I have with Professor Masberry, I fill up like 2 or 3 sheets of papers with footnotes. But yes, it's very clear what you said.
I should acknowledge that other people take a different view. This is not something where we have all reached an agreement yet. I think I've been reasonably consistent about it. Fernando may wish to say, no, you've changed your mind on that one. But I think it is about that, looking for a systematic way to solve problems that could be automated.
Temos uma mão no ar.
Yes, I have another question by António Santos. António, queres colocar tu ou queres que eu traduza?
Não, posso colocar a questão em inglês sem problema nenhum. Hello, teacher.
Yes.
Thank you for being with us tonight. There's an outstanding question to me. It's that everybody believes that teaching computer science and all things related to computers have to be based on pure and simple mathematics, and things can't work, can't be without one another. So I believe since the 1950s, the computer was able to make large computational amounts with ease, and even further with TTL logic, it still was simple. But it took us about 60 years, if I'm not mistaken, to teach a computer how to read a text. So is this still a myth, or is this myth still being true? We can't separate computers and math. Thank you.
My goodness, should we? So historically, Turing, who's the founder of computer science as an academic discipline, or Turing and Church, the co-founders of computer science as a discipline, was seeking to solve or prove a particular result in mathematics. The fact that in the English-speaking world we call it computing, computer science, computation is about finding the answer to some sort of mathematical problem. This is what Turing specified, is what doing mathematics means, and this defines computation in those terms. In much of the rest of Europe, the term is informatics, which suggests much more working with all sorts of types of information rather than just getting a number at the end of this. And, if we go back to the prehistory, before Turing's time, Ada Lovelace, yes, with Babbage's analytical engine, saying, wouldn't it be amazing if this could do lots of things other than just produce tables of numbers? What if it could compose music or write poetry? And so I think we have got that idea right from very early days that there may be more to it than this. One of the themes which I didn't talk about running through the English computing curriculum is this idea of how information is stored. We teach pupils to learn about binary numbers, that all information is represented as zeros and ones on the computer. We debated whether to include that or not. I was in the against camp. I said they should learn that it's about numbers, that the information is represented digitally. Binary is just details of implementation there. I lost, but never mind. And the idea that whatever we're working with can be represented as numbers, I think is foundational to computer science. But that doesn't mean to say it can only do maths. That somehow, because it's all reduced to numbers, I think there is a link with maths. The other thing I'd say is in studies in America say one of the best predictors for how well somebody does in undergraduate computer science is how good they are at maths. And I think there maybe still some connection there between the sort of reasoning that you need to do well in the maths curriculum and the sort of reasoning you need to do well in a computer science degree. But that could be because we have too narrow a concept of computing.
Actually, kind of interesting that you've mentioned Ada Lovelace being for us so important to bridge the gap and to even things out between male and female in computing, and also because about nearly 100 years ago, more or less, of course, give or take a few decades, she just came up with insights such as those, that computation does not have just to be about numbers. Any more questions? Mas alguém quer questionar? Fernando, então...
Penso que podemos encerrar, dar por finalizada a questão para o professor e a vida dele.
Foi bastante espremido. So, Professor, thank you. I deeply thank you for this moment. It was an honor. It was delightful. And I believe everyone that I'm seeing on this screen was enriched, deeply enriched by your talk, by your presentation, by this conversation that we're having amongst us. Again, thank you. I wish you a good evening over there in a land I really wish to be able to visit as soon as possible.
It's for Sophie, okay? For your Sophie.
Oh, yeah.
The honor has been mine. Thank you so much for the invitation and the time which you've put into listening to me just talk about all of these things this evening. It's been an absolute pleasure. And once again, my apologies that internet and indeed microwaves here have made this such a difficult experience for all of us. But that's over now. So thank you once again. I hope to visit before very much longer. I really do.
So do we. Thank you, Professor.
Right. I'll click the button. Bye-bye. Bye.
Goodbye.
Fazendo só um pequeno ponto de situação, não se esqueçam de marcar as presenças e de que a atividade para esta semana é partilhar uma aplicação ou um sítio com recursos para pensamento computacional, programação, robótica, realidade virtual, das 5 áreas que estão no projeto. É essa a atividade que tem para esta semana e a mim parece-me que a evolução da Inglaterra não é muito... o percurso na Inglaterra não é muito diferente do nosso, vamos sempre 3 ou 4 anos atrás, mas que as ondas vão para cima e para baixo, mais ou menos como cá. Temos aqui a Sara que quer fazer questões.
Boa noite, Fernanda. Quando é que abre o Padlet para colocarmos o trabalho?
Já está.
Já está. Ok, obrigada.
Só fazer refresh, F5, refresh e está desde o início da sessão.
Já vou lá ver.
Desde que o Filipe partilhou que eu abri tudo logo.
Ok, obrigada.
Está lá a atividade explicada e está lá o Padlet. Acho que está partilhado. Se não estiver, digam qualquer coisa.
Okay,
e pronto, boa semana para todos. Para a semana voltamos com mais uma sessão de pensamento computacional, desta vez são nós, para falarmos também das nossas coisas. Tá bom? Boa semana para todos.
Obrigada, igualmente.
Obrigada.
Obrigada.
Boa noite.
Boa semana.
Boa noite.